In the previous video, I taught you about conservative forces and energy. In this video, I want to talk to you about non-conservative forces, such as the force of friction and air resistance. These forces do depend upon the pathway taken. So if we look at this diagram again, we see two different scenarios. In the scenario with the arrow, this man is raising an object vertically from point A to point B. In the second scenario, this man is traversing 3 flights of stairs to get this object from point A to point B. Clearly, the second scenario is a longer path, and for non-conservative forces, this would greatly affect the energy associated with it. Now, I want you to go ahead and now look at this video clip, and I want to talk to you about changes in mechanical energy and how they occur from microscopic interactions. Now, I've spoken to you about this previously. These microscopic interactions that you see, in this case in a PHET simulation dealing with friction, you can see the thermometer, you can see the generation of heat, sound, deformation of these microscopic particles. So this is a really good example of how non-conservative forces can actually change mechanical energy in a system. Now, recall this schematic represents the surface of a table. And I showed you this back when I taught you about force normal. I showed you that when an object is placed upon this surface, there is a deformation that will occur. And this is actually the result of electromagnetic force. However, you need to simply understand that these forces and this dissipation of heat, if you will, arises from microscopic interactions. Here is a video clip that is showing a tennis ball being dropped. As you can see from this video, when the tennis ball strikes the ground, there is a deformation of its shape. This results in a decrease in the mechanical energy. As you can imagine, there's also some sound associated with this, as well as some heat dissipation through friction. So all of these non-conservative forces that occur when the object strikes the ground will decrease the overall mechanical energy of the tennis ball Earth system. Energy changes precisely by the amount of work done by a non-conservative force. So we will denote this work with a subscript of NC. And remember that mechanical energy is the sum of both kinetic and potential energies. So when we say the change in mechanical energy, we're referencing kinetic and potential energies. Also recall that a change in kinetic energy or potential energy is the final value minus the initial value. So if we expand these out to include final and initial values, and we add the initial values to both sides, we end up with the following equation. So let's do a practice problem so you can understand how this works. We have a 65 kilogram PC Patriot baseball player. He's running at 6 meters per second. He slides to a stop to secure the victory. However, while he's sliding, a constant 450 newtons of frictional force are exerted upon the player. You're asked to calculate the distance. So as always, I'm going to underline a couple key words here. Stop refers to his final velocity is 0 meters per second. And we're asked to solve for the distance. So this is a little different than what you've seen in the previous lessons. So if we look at the work done by friction in this instance, and we use the work equation, we can then plug in our value of 450 newtons given in the problem. We're trying to solve for the distance d, and then where does this cosine of 180 degrees come from? Well, the player's running and sliding in one direction, and friction always opposes the motion. This frictional force is actually anti-parallel to the motion. So that means that the angle between the force vector and the distance would be 180 degrees. And of course, cosine of 180 degrees is -1. So we're dealing with negative work, which simply makes sense that this would be negative work. And we're going to see a decrease in the mechanical energy of this system. So I'm going to go through and show you how I got this equation here. It's real simple, and I'm going to always do this in class. So with reference to our equation here, before our initial quantities, is there kinetic energy? Of course, the player is running, the player has mass. Is there potential energy? Is there a spring? No. So there's no elastic potential energy. Is there gravitational potential energy? Not if we don't want there to be, because we choose where to put the zero line. And we would intuitively place the zero line at the ground level. So now I'm going to mark that off. Is there a non-conservative force? Yes, there's the force of friction acting. And for our final quantities, we say, is there kinetic energy? Well, no, actually there's not. He stops, and therefore his final velocity is 0, which makes kinetic energy 0. Is there potential energy? Of course not. So we're left with no mechanical energies on the right side of our equation, which means we will set our initial quantities equal to 0 joules. Now you might say, where did this negative sign come from? Well, it comes from the fact that we know this is negative work, as I just explained. So as we did in the dynamics unit, I like to take my negative works and subtract them from this, in this case, the positive energy. And if you want to add a negative, it's the same thing. So do what works best for you. This means that we can say 1/2 mv squared is equal to the work done by a non-conservative force, and therefore it is equal to 450 newtons multiplied by the distance. So now we can just do a little algebra here and solve for the distance to be 2.6 meters. That's how far he slides to secure the victory. So in this video, I taught you about non-conservative forces. I taught you how they can change the mechanical energy of a system. So now that you've learned about both conservative and non-conservative forces, it's time to put all of this together and talk about the law of conservation of energy. And I'll see you guys in class.